Okay, so welcome back. In this lecture, we're going to discuss the Jointree algorithm. And the Jointree algorithm is a very popular algorithm for inference in Bayesian and Markov network. The Jointree algorithm belongs to a different class of inference algorithms. So we haven't seen variable elimination, and the main idea was to eliminate one variable at a time. You're going to see now a new class of inference algorithms that instead of eliminating one variable at a time, you're going to eliminate one factor at a time. So we call those algorithms factor elimination. And the main advantage of the Jointree algorithm over the variable elimination algorithm is in the case that you want to answer multiple queries over multiple set of variables. So imagine a situation that you just don't want to query your Bayesian or Markov network to a single query, but you want to run multiple queries over different sets of variables in those networks. And we're going to see that the Jointree algorithm, it allows us to answer those queries with the same complexity of just one call of the variable elimination algorithm. Okay, the Jointree algorithm is very similar to variable elimination that we call here in this slide the VE. This algorithm is also known as the click tree or the tree clustering algorithm. Especially when we work with Markov networks, we're going to see that it is better known as the click tree algorithm instead of the Jointree algorithm. And the main idea is that we can rethink what we know about the variable elimination in terms of factor elimination. So we can think about one algorithm that we're going to choose one factor, and we're going to eliminate that factor by multiplying the factor to another factor that we have in the network. And okay, just this change of view is not enough to justify the algorithm, but the truth is that the factor elimination algorithm, the Jointree algorithm, is so popular. It's because it's improved variable elimination in terms of complexity. And I'm going to see that the complexity for running the Jointree algorithm is the same as the complexity of the variable elimination algorithm. But the Jointree algorithm creates a data structure that we call the Jointree that will store the answers for different queries. So we're going to use that data structure to answer multiple queries over different parts of the network. And that is the main benefit of using the Jointree algorithm instead of the variable elimination algorithm. There is also another reason, and it's the fact that the Jointree algorithm and also the idea that we're going to discuss in this lecture, that is to make inference using the message passing paradigm, is going to be the basis for a set of algorithms that we're going to discuss in the next lecture, known as the belief propagation algorithms. Those algorithms are going to be different because they will not be exact algorithms. They're going to be approximate algorithms, but they can provide some good results with less time for doing the computations. So we're going to start this lecture by discussing the idea of factor elimination, and we're going to improve our initial algorithms that I'm going to propose with this idea until we get to the point that we will propose the final Jointree algorithm. And I'm going to see a few examples of this algorithm working for both Bayesian and Markov networks. So let's suppose that we have a network and we want to compute some posterior marginals for each of its n variables. So something that we can do is to run variable elimination algorithm multiple times. So we know that if you run variable elimination just once, the complexity is going to be n times 1 exponential over w, and w is the width of the elimination order. So this is the complexity, and we have discussed this in the previous lectures. So if you have any variables and we want to compute those posterior marginals for each of these any variables, so what we're going to do is to run this algorithm n times, and the final complexity is going to be n squared and exponential over w. And one problem here is this n squared term, and it can make the inference quite slow even for the situations in which the tree width of the network is small. So we would like to eliminate this n squared term and make inference more efficient. And one possibility is to use the Jointree algorithm. So the Jointree algorithm will answer those posterior marginals for each of the n variables with a complexity that is also n 1 exponential over w. So this is the same as just one run of the variable elimination algorithm. And the idea here, and we're going to discuss this during this lecture, is that we can save the partial computations into a data structure that we call the Jointree, and use later on the data structure to answer the queries. One limitation of the Jointree algorithm is that it cannot answer queries over arbitrary sets of variables. It's going to be over some predefined set of variables. And it sounds like a very strong limitation in the beginning, but you're going to see that this algorithm is going to be very useful in several situations, particularly when we are learning from data. So it's going to be a very useful algorithm for certain situations. And also, we're going to see that we can manipulate the Jointree, making operations over the Jointree, so we can set the clusters of the Jointrees, and I'm going to discuss this more in detail later on, with set of variables that we choose, so we can answer certain queries that we needed to. So, but we're going to discuss this idea in more details later on. In principle, the Jointree will answer the posterior marginal queries over all network families for the Bayesian networks. And a network family is a variable and its parents. So we will be able to answer posterior marginals over the set of variables A and B. It is one family. Another family is A and C. Another family is C and E. Another family is B, D, and C. In a similar way, for Markov networks, we're going to be able to answer posterior marginals over cliques of the network. So we're going to be able to answer queries over A, B, and C, and also over B, D, and C, and also over C and E. Okay, but before we discuss the Jointree algorithm, let's start in discussing one much simpler algorithm based on the idea of factor elimination. So the idea here is that we're going to compute a prior marginal, so there will be no evidence involved, over a single variable Q. And if we use the variable elimination algorithm, what we're going to do is to eliminate all the variables that we have in the network but Q, and in the end we have the probability of Q. And factor elimination is going to be something that is similar, but instead of working over variables, we're going to work over factors. So you're going to eliminate all the factors except the one that mentions the variable Q. And the elimination of one factor is going to be a two-step process. So let's suppose that we want to eliminate the factor fi from a set of factors s. What we're going to do is to take the variables that only appear in fi, and we call this set of variables v. And that's going to be very similar to what we do in variable elimination. We eliminate one variable when we have a multiplier all the factors that mention that variable. In this case here, we seen that the variables in V, they only appear in factor fi. And as we are going to eliminate this factor, we can also eliminate those variables. So we compute this, it's going to be the sum over V for the factor fi. So I'm going to eliminate all the variables that are in V. And we're going to take this resulting factor and we're going to multiply by another factor that we choose, that is calling this fj. And fj is one of the factors that are remaining in the set S. So let's take a look at the next slide, and I'm going to see how these work in the form of one algorithm. Okay, so this is our first factor elimination algorithm, and we're going to call it FE1, and we're going to improve this algorithm later on as we discuss more details about this idea of inference. And this factor elimination algorithm will receive as input one network n, one single variable q, and we're going to return the probability of q. So it's going to be a prior marginal. So there is no evidence, and it is a single variable q. So it's a very simple situation, a very simple example, and we're going to improve this algorithm later. So what are you going to do? First, we're going to call S the set of factors that we have in the network N. We're going to call FR one factor that belongs to S and contains the variable Q, the query variable. And now we're going to start the elimination process that we're going to eliminate one factor over time during this while loop here. So the idea is to continue this loop while S has more than one factor. So I'm going to eliminate all the factors until we have just one factor that's going to be FR. In this case, we're going to return the marginal P of Q by eliminating all the variables that we have in FR but Q. So the idea is to remove one factor Fi that is not FR from the set S. So I'm going to pick one factor there that is not FR, and FR is the factor that has the variable Q. So I'm going to choose another factor that is going to be eliminated. And we're going to call V the variables that appear only in the factor Fi, but they do not appear in any other factor that is in S. So these variables in V are exclusive to Fi. And it means that we can eliminate those variables, right? So remember from variable elimination that before eliminating one variable, we have to multiply all the factors that mention that variable. So in this case here, we have already eliminated all the other factors. The only remaining one is Fi, and I'm going to eliminate this factor. So all the variables that are still there, they are still only in Fi, can be eliminated. And that is what we're going to do in the next step. So in the next step, we eliminated the variables V that are in Fi, doing a summation. So I'm going to sum out all those variables, and I'm going to take one extra step. Then I'm going to multiply the resulting factor by Fj. And Fj is another factor that belongs to S. And I'm going to continue doing this until we have just one factor that's going to be Fr. In this case, we stop the loop while, and I'm going to return what we call the projection of Fr over Q. And this projection is just another elimination of variables. We're going to eliminate all the variables in Fr and going to remain with just the variable Q. So we have the equation here for this idea of projection, and we can see that it is a summation that it mentions all the variables in F, but the variables in Q. And that concludes the algorithm. So let's discuss a little bit why this algorithm works, and I'm going to take a look at one example. We're going to go through all the computations in detail, so we're going to double check our understanding of the algorithm. Okay, it should be clear now why the factor elimination algorithm works. And it's very similar to the variable elimination algorithm, with the exception that the variable elimination algorithm eliminated one variable at a time, and the factor elimination is going to eliminate a set of variables at once. So we're going to eliminate all the variables in V at once. But we are very careful about which variables will be in V. We only eliminate the variables that are in the factor Fi that I'm going to eliminate. So these variables are only occurring in this factor and not in any other factor that we still have in the factor elimination process. So it's guaranteed that we can eliminate those variables because there are no other factors mentioned in those variables. So as these variables, they only appear in Fi, we can replace Fi by a new factor that's going to be the factor Fi after the elimination of all the variables V. And something that is slightly different from the variable elimination algorithm is the fact that we take one extra step. We take this resulting factor and we're going to multiply by another factor that we call Fj. So we do this extra step and we multiply the new factor, it's this one here that we just eliminated the variables V, by another factors that we call Fj. So it's clear that at each iteration of this algorithm, we're going to eliminate one factor. So we're going to decrease the size of the set S that has all the factors by 1. And after enough number of iterations of this algorithm, this set S will have only one factor, and this factor is the FR, is the factor that mentions the variable Q. As we have this final factor, what we do, we eliminate all the variables that we have in this factor FR, but the variable Q, and then it's gonna give us an answer to our query. Reminds that the initial factor elimination algorithm, we're gonna answer queries in the form of the probability of Q, and Q is a single variable, so that's why we are doing this way. So we can see that we have two open choices here. One is which factor we're gonna select from S to be the next one to be eliminated, and we also have to choose which factor we're gonna multiply by, and that's gonna be the factor Fj. So we have these two open choices, and we're gonna see that these two choices do not impact in the correctness of the algorithm. So we can choose any factor to be the next one to be eliminated, and which factor we're going to multiply by, and this will not impact in the final answer of the algorithm, but it will impact in the complexity of the algorithm. So in a very similar way to the variable elimination, where the elimination order of the variables is important, in the factor elimination, the elimination order of the factors will also be important for the running time of the algorithm. So okay, it's always good to take a look at one step-by-step example to check if we are understanding the things correctly. So let's suppose that we have this very simple Bayesian network that have just three nodes, A, B, and C, and we wanted to compute the probability of C. And let's suppose also that we are going to starting eliminating this factor here. So the idea is, first, we eliminate all the variables that are only in this factor, and after we do that, we multiply this factor by another one. And if you look at this first factor here, it mentions variable A, and the problem is that the variable A is also mentioned here. So we have variable A and variable A here. So we cannot eliminate the variable A yet, right? That's very similar to variable elimination, where we did not eliminate the variables until we have multiplied all the factors that mention that variable. So in this case here, our set V is going to be the empty set, because we cannot eliminate A, and it's the only variable that is in this first factor here. So we do not eliminate the variable, and we multiply this factor by some other factor that we have in the network. And let's suppose that we're gonna multiply by this middle factor here, that is the factor that mentions A and B. So we do the multiplication, and that multiplication is what we already know. It is the join operation that we implemented in the tutorials. It's basically a multiplication of the entries that are compatible. So let's take a look at this in the next slide. So here is the operation. So let's just double check to see if it's correct. So for instance, this entry here mentions A true and A and B true. So we're going to multiplication of 0.6 by 0.9, 0.54. This entry here mentions A and not B. So we're going to be multiplication of this one by this one here. Going to be 0.6 times 0.1, going to 0.06, and continues doing that for all the entries. So we have as resulting factor this factor here, that is the multiplication of the factor A and the factor B. That's why we are calling FA FB. So notice that we have one less factor, right? So we basically eliminated this factor here. What we have is still the result of the multiplication of the factor FA by this factor here, and we also have this factor here. So we go to the next step of the algorithm, that is the elimination of one more factor. And in this case, we have to choose this factor here to be eliminated, because this guy here is basically our FR, is the factor that must remain until the end of the execution, because it mentions the variable C, that is the query variable. So let's take a look on the next slide. Okay, so we have here these two factors, the two remaining ones, and I'm going to eliminate this factor here. So this factor mentions two variables, a and b, and a only occurs in this factor. It does not occur here, so it's going to be exclusive to this factor here. That's great. So this is the time that I'm going to eliminate this factor, and remind that the elimination of a factor is a two-step process. First step is to eliminate all variables that only belong to this factor, and the second step is to multiply by another factor. In this case, we have to multiply by the factor fc because it is the only remaining factor that we have. So we start by eliminating the variable a, and that's a very simple process. What we do is to look at the variable b, and you have here the b true and b true, and we sum over all possible values of a. They're going to be a and not a, and that's going to be this entry here, 0.54 plus 0.8, and the other entry is going to be these two guys here, 0.32 plus 0.06, and then going to be this 0.38. So we eliminated the variable a. Now we have a factor that only mentions the variable b, right? We're going to call this the sum over a, fa, fb, and we have this resulting factor that we're going to multiply by another factor that is the only remaining factor, that is fc. So I'm going to do this multiplication in the next step, in the next slide. Okay, so we are here. So this, again, we have done this several times before, is the multiplication of these two factors. So when we multiply these two factors, we get this factor here that mentions variable b and c. Remember that this guy here mentions variable b, this guy here mentions variable b and c. The resulting factor must mentions variable b and c. And we have this resulting factor here. Okay, what we have to do now is the last step of our algorithm, because now we have just one factor remaining. So we're going to stop with the while loop. We're going to leave the while loop, and we have that final step, that is a return the projection of this factor over the variables in Q, and in this case here is going to be the variable c. So what I'm going to do is to eliminate the variable b, and we're going to get just one factor that only mentions variable c, and here it is, right? So it's going to be the final step, and we're going to sum these two factors here, these two entries here that have the value true for c, and these two entries here that have the value false for c, and we get this final factor here that's going to be our answer. So this is the probability of c that was our initial objective. Okay, so I think that's a good time for a break, and we will continue in the next video introducing the idea of the elimination trees that are going to impose an order for the elimination of the factors. So see you soon.